Okay, we're going to move to the last part of our lecture series on DC circuits. This is on potentiometer application. But before that, I'm going to show you a simulation that one teacher in Singapore created to explain, help you visualize how a potentiometer work. Right, let me just switch to it first. Okay, let me just toggle it on. Right, so you see this setup here. You have basically your driver circuit, this 12-volt cell connected to this resistance wire 1 meter long, and then it's also in series with 2 ohm resistors. So you can, this resistance wire has a resistance of 1 ohm. So if you want to, you can see that this whole length will take out 1/3 of the total resistance, because it's 1 plus 1 over 1 plus 2, I get 3 ohms. And then yeah, this is 12 volts, so this will take up 1/3 of this 12 volts, so this 4 volts. Okay, I can adjust the bottom EMF, so I can set this EMF over here to different values. So let's say just set it to 1.5 for now. Right now, I can adjust my jockey position until I get a null deflection. Okay, how do I know in this simulation that I get a null deflection? We'll see later. But right now, you can see that as I shift if I shift my jockey to the right hand side, the resistance R1 is increasing. Alright, and then this R2 is also decreasing. And this VR1, which is the potential difference across R1, is also increasing as I go. Right, so I just need to get it balanced. If I shift it to the left, okay, because this value is quite small, so if I shift all to the right, there's nothing. If I go all the way to the left, go all the way down, somewhere around here, you see that the arrow appears. That means this galvanometer is now giving you a null deflection. Right, so this length of 0.375 meters will give you null deflection. Okay, of course I can change the EMF of the bottom cell. Let's make it 2.5 now, and nothing on the left is going to give me the same to give me a null deflection. So I'm just going to push it all the way to the right hand side and just go slowly until I hit it somewhere here. Alright, this is when I get null deflection at 0.625 meters. Alright, so with this in mind, you can try it later on your own if you want to. I'll put a link inside the SLS page. Right, let's go back to our PowerPoint slides itself. Okay, so going back to this, let's go on. Right, let's just show my cursor first. Okay, we are looking at example 10. Example 10 has 4 parts. This is 10A. This is the simplest one. In the circuit shown, cell A has an EMF of 2.0 volts and negligible internal resistance. Wire XY is 1 meter long and has a resistance of 5 ohms. Cell B has an EMF of 1.5 volts and internal resistance of 0.8 ohms. Calculate the length XP required to produce 0 current in the galvanometer G. Okay, so right now you can see that this length here XP is part of this wire XY. So VXP is the one that will balance the 1.5 volts. So I need my VXP to be equal to 1.5 volts. The internal resistance here does not matter. So let's just check it out. Okay, so VXP is equals to EB, EMF across B, and that is equals to 1.5 volts. Alright, and then the driver circuit, there's no other resistance except for wire XY. So the VXY is equals to 2.0 volts. All the PD provided by cell A is dropped across XY. Okay, and then hence using potential divider concept, EB is just equals to VXP, and this is equals to L length of XP divided by length of XY multiplied by VXY. Alright, and that will give me 1.5 equals to L over 1.0 times 2.0. So LXP will give me 0.75 meters. Okay, so this is the simplest setup over here. Okay, next we'll move on to internal resistance in the driver. Right now your cell, okay, I didn't change the question, but you just look at the diagram. So right now there's internal resistance in the driver. I'm going to add the internal resistance in. There's a 1.0 ohm internal resistance here. So right now this driver circuit has 2 resistance, one of wire XY and the internal resistance 1.0 ohm here. Alright, so the most of the PD will be dropped across XY, but not everything, because some of it will go through the 1 ohm instead. Right, so since again this is now deflection, my VXP is equals to cell B. Right, same thing. This is still equals to 1.5 volts. Okay, like I said, the internal resistance of cell B does not matter. Alright, so in the driver circuit, there's internal resistance of 1 ohm. Alright, so my VXY, the potential drop across XY, is resistance of XY over resistance of xy plus internal resistance multiplied by EMF provided by cell A. And this will give me 1.67 volts, right? So 1.67 volts across VXY, then I need to find the balance length of XP using the potential divider concept again. We find EB equals to VXP equals to LXP over LXY times VXY. So basically, this potential difference is equals to this length divided by this length multiplied by 1.67 volts. All right. So if I do it this way, then I get if I do the same calculation, I realize now my balance length is higher now, 0.90 meters. It's because right now XY does not have the same potential drop as beforehand. All right. So this 10B. 10C, we are looking at series resistor in the secondary circuit. Okay, so again, I'm going to show you the animation of where the extra resistor will go into. This is in series connection, so it will go into here, this 1 ohm resistor here. So this 1 ohm resistor, because remember I said no matter what internal resistance here, it's not going to matter, because as long as this EMF is equals to this VXP, right, it will still be null deflection. Even if you have a very small potential difference, the difference between this cell B and this EMF, let's say about 0.001 volt, right? Because my galvanometer is sensitive enough, it will still pick up the very small current. Alright, so basically there's no change in the answer here. So since null deflection, resistor in secondary circuit has no current through it. If no current goes through here, there's no potential drop through here, and no potential drop through here as well. So basically this VXP is still equals to 1.5 volts. Alright, and the answer will be same as part 1, 0.75 meters. Okay, no change. Alright, we move on to the 10D, which is perhaps the most complicated. Okay, 10D, I add a resistor in parallel in the secondary circuit. So this is what I'm going to do. I'm going to add the resistor below here like this, a 1 ohm resistor below. Okay, right now this one is a bit hard to analyze, but we can still do it. Okay, here right now, we are measuring, okay, this 1.5 volts here, right? The EMF is spreading across part of the PD, part of the potential drops across here, part of the potential drops across here. So right now, when you go from this end, from X to P here, right, you are measuring the terminal voltage across the 1 ohm cell. Okay, so this reading here, this whatever the PD across here is a PD across XP as well. Okay, so the 1 ohm cell forms a parallel branch in the closed loop cell B, hence there's current flow in secondary circuit. Okay, so the current is flowing through the secondary circuit in this manner. Alright, that means now your terminal PD across cell B, which is from this point to this point, is the PD across the 1 ohm resistor. Okay, then we can apply potential divider concept here first. So the potential across this 1 ohm, the potential difference across this 1 ohm is 1 ohm over 1 ohm plus the 0.8 ohms over here. So this over this section here is a potential divider concept as well. So, okay, so I'm taking the potential difference across this 1 ohm. This PD is equals to this PD, which is also equals to this PD. If this PD is not equals to this PD, this galvanometer will deflect. Alright, so we don't want that. So right now my V1 ohm is 0.83 volts. That means my VXP has to be equals to 0.83 volts as well. Again, this is the case where you have no other resistance in driver circuit except for XY. Okay, so VXY is 2 volts. Then we balance this again. V across the 1 ohm must be equals to the terminal voltage across cell B, which must be equals to VXP. Then this is LXP over LXY, same as just now, times VXY. So you submit the value, 0.83 equals to LXP over 1.0 times 2.0. So my LXP now is 0.42 meters. Okay, so this is the most complex example. You may want to take a bit more time to look at what's happening here. Alright. Next, we move on to example 11, which is our last example here. The diagram shows a circuit which may be used to compare the resistance R of an unknown resistor with a 100 ohm standard resistor. The distances L from one end of the potentiometer slide wire to the balance 4 millimeters and 588 millimeters when X is connected to Y and Z respectively. So the length of the slide wire is 1.00 meter. Find the value of resistance R. So here, the aim is to find out this resistance here. Alright. Again, I cannot just tap a voltmeter directly across it because there is internal resistance here. Part of the there is the voltmeter will have some resistance as well, so it will not give you an accurate reading. So right now what's happening in the question is that when I connect X to Y, the balance length is equals to 400 millimeters. When I connect it to Z, the balance length is 588 millimeters, alright, out of 1 meter. Okay, so let's look at what we can do here. Let's do for the first one here. Okay, at balance condition, the PD across balance length wire length L is the same as the PD across resistance in secondary. So for example, right, if I connect X to here, when it's balanced, right, this potential drop across the resistance wire, right, the sectional resistance wire, is equals to the potential drop from here to here. Okay, so remember this end is a higher potential. That means this end, and this end at the higher potential. Okay, right. Okay, so moving on, when X is connected to Y, okay, let's solve this equation. So when X is connected to Y, right, I'm tapping, okay, 0.4 meters over 1 meter times E1. That means this is the section, this is the potential difference across the 400 millimeters. And this is equals to 100 over 100 plus. What's 100 over 100 plus R? Because right now, the total resistance here is 100 plus R. Okay, so this potential drop from here to here is E2. Okay, and then again, we know that there's internal resistance here, but it doesn't matter because the potential drop from this 100 from here down to Z is always a constant value. Okay, so we just assume that there's no internal resistance, right? We just take as E2. But again, if there's internal resistance, it will be some other value less than E2, but it will still be a constant value. So I tap it here. I'm just tapping the potential across the 100 ohm. Okay, so this will be the 100 ohm over the 100 plus R. So 100 over 100 plus R times E2. So this is my first equation here. I have three unknowns. I have three unknowns here for now. Okay, but let's just leave it first. Okay, then we're gonna do the second one when X is connected to Z. When it's connected to Z, my length is 0.588 meters over 1 meter times E1. Because now I'm tapping both resistors here, I'm essentially just tapping E2. The potential difference between here to here is E2. Alright? So I have equation 1 and equation 2. I'm just going to divide one by the other. Okay, then if that's the case, if I go and resolve this, I get 0.4 over 0.588. And this is equals to 100 over 100 plus R. Okay, because this whole thing 100 over 100 plus R divided by 1. Okay, so you can just solve this and get R equals to 47 ohms. Okay, so please take time to study example 11 and example 10, example 11. It takes a bit more to comprehend it fully. If you're and try the rest of the SLS package, and you can start on your tutorial as well. Okay, with that, that's the end of the lecture series. We will see you for the next chapter, which I believe to be magnetism. I think EM. Right, thank you.